Ladies and gentlemen, welcome to lecture number, God knows what, it's 22, I think. Well, in this lecture, and this will be the last lecture from this chapter, we will talk about optimization problems in physical sciences, engineering, business, biology, well, so many applications we will see of derivatives. Let me just dive directly into the subject. So I would like to show you some applications where we use the first and the second derivative tests, and I think I sent you already some material in advance, and you know what to expect. Well, let's see what is optimization all about. So like I said, we will see real-world applications, and we would like to see how to deal with these applications when and how to relate them to derivatives. So what is optimization first? So optimization is the process of finding maximum or minimum of a function, right? So that's what we're trying to see. So when we have a real-world application, I don't know, from engineering or whatever, we will try to express those quantities in that particular problem as a function of something. I don't know, maybe if something is moving, maybe of time. Usually it's a function of time or something like this. Or I don't know, something. If something is variable, we will usually take a function of that. Well, let's see the first example. And the first example I have in mind is the following. Look at this guy. So this is example 1. I believe we have done a couple of these, right? In the past, we've talked about related rates, remember? But we haven't used derivatives there. So basically, it's more or less like exactly. So we did a few about box volumes and stuff like that. Yeah, exactly. But now we have something like this. So let's read the first example. So a farmer has 2,400 feet of fencing to build a rectangular, and that's a very important information, rectangular pen bounding a straight river on one side. Well, we're asking, it's a natural question to ask, what dimensions give the greatest area? So he'll try to maximize the greatest area. So how would we think about this problem? So what is the first thing that so when we analyze this, right? So the first sentence, let's say, well, it's actually one sentence, but let's say the first part of the sentence. What does it say? It says that a farmer has 2,400 feet of fencing to build a rectangular pen. So this is the word here, rectangular. So in other words, we're dealing with what? With a rectangle, right? So maybe we should know some things about the rectangle. All right, great. So, and we're asking, what is the greatest area? Of what? Of the dimensions of the rectangle. Great. And what do we know? We know that a farmer has 2,400 feet of fencing to build. So how we can translate this? So I'm wondering how we can translate this here. So at this point, we do have enough information to translate this problem. So first thing first, what did we say when we dealt with related rates problems back a few lectures ago? The first thing that we need to do was what? Was to draw a picture, right? Do you remember that? So we need to draw a picture. All right, great. So, and how can we translate that, this first part of the sentence? So a farmer has 2,400 feet of fencing. So in other words, let me draw the picture. You see, we have this is a rectangular pen. And we know that the dimensions are, well, it's a rectangle, right? Of dimensions X and Y. Let me just draw it again. Look at this guy here. You see, this guy here. So this is a rectangle. And also this guy here, ouch. That's not a straight line, but anyway. I didn't claim I was an expert at drawing, but, and you see, this guy here is also X. So this part from here to here. So we're dealing with the rectangle. And what do we know? Can you tell me? So, but before we go into that, what do we need to find? So we need to find the greatest area, right? And what is the greatest area? So keep in mind that this is what we want to find, the dimensions of the greatest area. So what is the area of the rectangle? Do you remember? Exactly. Right. So in our words, how using our notation, it will be what? X times Y, right? So X times Y, right? Okay, great. Or the length times the weight. Yeah, exactly. It's the same thing. Anyway, so that's the area of the rectangle. So we need to find a formula for the quantity that we would like, we want to be optimized. So in our case, we would like to optimize the area, well, the greatest area. So that's it. A will be, and as you can see, A is X times Y. All right, great. But, so the dimensions are X and Y, and I would like to optimize, I would like to find the maximum area. So in other words, I would like to see when that product XY is on maximum, right? Is the greatest. That's exactly. I would like to see for which X and Y this happens, right? All right, great. All right, now let's go back to the first line. A farmer has 2,400 feet of fencing to build. How we can translate this? Because the fence, we already said that it's a rectangle. Because we need to have some kind of a constraint, right? We want to this quantity A X times Y to be optimized, right? We would like to find when is the largest and for which X and Y this happens. But we will also we would also want to see what kind of constraints are between X and Y. In other words, what kind of a relationship between X and Y is between these two? Exactly, the perimeter. And how can you yes, exactly. So is the perimeter, right? But pay attention because it's a fence, right? So in other words, so we would like to use constraint to express the quantity in terms of a single variable. And what are we going to do? So this portion right here, this guy here, can be translated into what? Into a, exactly. So pay attention because look, here is the river, so we don't need this. Let me just look. Here is the river, so you just put there. You don't need that thing over there, right? It's already the river here. Here is the river already, so you don't need that. So we're going to take this, so it's going to be x plus 2y, you see? So that's how we're going to translate this. So this will be translated into this. So x plus, in fact, let me, so this will be translated into this. So the constraint is that 2y plus x is 2,400, right? You see, I have only these portions here. Only this, this, and this. Because here it's a derivative, so I don't need that. So it's more or less like a perimeter, but it's missing, the base is missing. So that will be the constraint. In other words, we would like to optimize, to maximize this quantity x times y when x plus 2y equals 2,400. But now, here, we don't like to deal with functions of two variables. You know, you'll learn that in Calculus 3. So we would like to express x in terms of y, or y in terms of x, and then we can replace this into the first formula. So what are we going to do? So we're going to write y. So y will be 2,400 minus x, everything over 2. Great. And we're going to plug it into the area formula. So let's do that. So the area, and this will be a function of x. So this is a of x. So once we plug this guy here, right, we're going to plug it in here for y. We're going to end up with this. So a of x is this function. It's, by just doing the algebra, it will give you 1,200x minus 1/2 x squared. So what do we need to do? We need to maximize this function. But first, before we even do this, we need to see what is the domain of this function, right? This is important. So what is the domain of this function first? So where is this function defined? So a is defined on what? Can you tell me? Takes values from what? From 0 to 2,400, right? And real value. So that's my function. So I need to maximize this. And there are plenty of ways of doing this. You don't even need to use derivative to do such a thing, right? You can do it even without derivatives. So you have no problems. You know where the max or the min of a quadratic function is. You can find it. But, well, you don't want to remember that. So maybe you will just take the derivative, set it equal to 0, you find the extreme point, and so on. So let's do that. So this is in step 3, so we're going to set up the problem. We know what the function is. And now in step 4, we need to find the optimal value of this. So what are we going to do? To find the optimal value, I would say, we need to solve the equation a prime of x equals 0. So in other words, we need to take the derivative of this guy. So let's write it here. A prime of x is what? It's 1,200 minus what? Minus x, right? So that's the first derivative of that function, right? All right, great. So we're going to set it equal to 0. So as you can see, the derivative of a with respect to x is 1200 minus x. We're going to set it equal to 0. And I think this is quite clear. It will give you x to be 1200, right? And now the last step, what we need to do is we need to determine the max, right? So how are we going to determine the max? Well, I want you to tell me. So this is the critical number. But remember how do we determine the relative min, relative max? Remember that this function is defined on this interval, you see? It's defined on the closed interval 0, 2,400 in real value. So what do we need to evaluate? We need to evaluate a at what points? Can you tell me? What did we say? When we have a function defined on an interval, now we need to determine the relative min and max. So we evaluate the function at what? At the critical numbers and at what else? Come on, tell me. At the end point, exactly. Oh, yeah, fine. Don't leave me here by myself, please. Yes, exactly. At the end point. Great. So that's how we're going to determine the max. So, like I said, the max can occur at the above critical number or at an endpoint. So we need to evaluate this one. What are the endpoints? So in this case, we need to evaluate a of 0, a of 1200, and a of 2400. So we need to evaluate these three. Great. A of 0 is 0. No question about that. Just don't forget what your function is. It's right here. So when you plug it in x0, it will give you 0. Now when you plug in 1200, it will give you this value, right? And then when you plug it in 2400, it will give you 0 again. So can you tell me what is the maximum and when is this attained? So what is the maximum value? Which one from these three we choose? We choose this one, right? That's the max. This is the max we're looking for. And when is this attained? Well, so the maximum area is 720,000, right? So it is attained when x is 1200 and y is 600 feet, right? All right, great. So that's the problem. So this is how you deal with these kind of problems. Let's see, do you have any questions so far? Is it clear what we did? I bet it is clear, crystal clear, huh? Let's do one more example. So in fact, let me go back a bit. Let me just explain the philosophy. So like I said, you see you have a fencing to build, and this fence looks almost like a rectangle, almost, because it's missing the down. You see that part over there is missing because it's bounded by a straight river on one side. So that's another thing to take into account. And we would like to maximize the greatest area of that thing. All right, so you know what is the area of the rectangle, and you know how to express that in terms of the so-called perimeter. but it's missing one part, so it will be just 2y plus x. You know that this is 2400, and then you keep going. You can write one of them in terms of the other, and you can plug it in, and then you have a function, and then you need to find the max, the relative max or min of that function, and that's it. All right, now let me show you another application, and this will be more for chemical engineers. Look at this guy here. So we like to design a 1 liter oil can shape can shape like a right circular cylinder. So what are the dimensions that we will use the least material? So in other words, the least material, what can we do here? So when we hear about the least material, you're wondering about what is this? Maybe it's a minimum of a function, right? But we would like to see what kind of function. So what are we interested in? So let's draw a picture. So this is the cylinder. You see it here, right? A circular cylinder. It has a height, as you can see. This is the height here, h, right? And the radius of the base, which is a circle, is r. And what we would like to do is to find when we want to use material, and basically we're asked about the surface area, right? So what will be the surface area of this cylinder? Well, the formula is given by this. So it's 2 pi r squared, right? So as you can see, we have 2 circles there, and we'd like to see all for the area, the surface area. So you have two circles, right? So the surface area for those is pi r squared for each one of them, and then when you add them up, you will get 2 pi r squared. And then what's left, right, of the cylinder, except those 2 at the top and bottom, you will the area is 2 pi r times h, right? So in other words, we need to minimize this function, right? We want to see the least material used. And what do we know? So you see, we know that 1 liter is what? It's like 10,000, or it's like 1,000 centimeters cubed, right? So we would like to use this constraint. But maybe we know something about the volume of this circular cylinder. And the volume, let me remind you. So in step 3, we would like to use the constraint to express the quantity in terms of a single variable. And let's do that. And let's keep in mind that 1 liter is like 1,000 centimeters cubed. And now we know that the volume is 1,000. So the volume of this circular cylinder is V is pi r squared times h, right? That's the volume, which is 1,000. All right, great. So this is 1,000. And now what we know this, right? So we know that we know this. And what we would like to do is to find out this guy. We need to take care of this guy here, right? About this function. All right, great. All right, so maybe we can replace some things. Maybe we can write h in terms of, as you can see here, we can write h as 1,000 over pi r squared. And now we can plug it in into the first one so that we don't need to deal with 2 variables, r and h, only one. And let's do so. And once we do that, So like I said, we have this h. And now if we plug it in into this formula here, right? Into this one here. So again, we plug in h, this guy, and then we'll get what? So the first part contains only r, so we don't have any problems. So it's 2 pi r squared plus the second part is 2 pi r times h. But as you can see, this guy here is h. You see, this guy is h. And once we do the algebra, and we'll end up with this function here. So a of r, let me rewrite it. A of r is 2 pi r squared plus 2000 over r. And now, first thing, so that's the function, that's a variable r. And now here comes the question. My question to you, what is the domain of this function a? Do you see any constraints or anything like on the domain or? So what do you think? How is this function defined? Well, you don't see any problems, right? So maybe this function will be defined on positive infinity r, positive 0 infinity, sorry. So a will be defined on the entire positive real line. So that's my function. So I have this function. I need to take good care of it, this function. Now, what do we need to do? Well, we would like to find what? The optimal value. So how are we going to do that? We're going to compute the derivative, right? So the derivative, let me write it here, a prime of r. So the derivative with respect to r is what? Is 4 pi r minus 2000 over r squared, right? So that's the derivative of my function. All right, let's do it. So that's the dA over dr. So the derivative with respect to r is this. And then we're going to set it equal to 0 because we like to find the critical number. And now once we set this equal to 0, as you can see, we have this equation there that we need to solve. 4 pi r minus 2000 over r squared equals 0. Great. Oh my, and now by doing some great algebra, which I don't want to do, thank God the slides do this for me. So we have to solve this equation, and then this will give us the solution for this equation is given by this guy here. So r is this here, and of course, so that's the critical number. And of course, we can express h as well. So r is something like cube root of 500 over pi, something like this. And h will give you, because you know what is the relationship between them. Let me go back. You see, it's right here. So h is 1000 over pi r squared. So once you know pi, or once you know r, you know h as well. So h will give you 1000 over pi times cube root of 500 over pi, everything squared. Or if you want to replace this by its approximate value, you can do that. And as you can see, you have the approximate values for these two. So for r is 5.42 centimeters, and for h is 10 point around, well, more or less 10.84. All right, great. So this is the critical number. We haven't decided if it's a min or a max. So we have to see if it's a min or a max. So we need to prove that. So that's the first step 5, because we found the critical number, and we would like to see the critical value. So, but we would like to see what kind of critical number is this? It's a min, it's a max. So what do we know? So this critical number, right, this critical value, the question is what happens? So, okay, let me ask you this. How are you going to decide the faith or this critical number R? In other words, how are you going to decide if it's a min or a max? How? Tell me. Wow, somebody's singing his guitar, Dylan. No, you can sing, it's fine. I don't mind. You can sing something to us as well, you know, not just yourself. No? Too bad. I wanted to hear something. But like I said, I don't mind as long as you pay some attention here. That's good for me. That's good with me. I'd rather you play the guitar, or rather than do some other activities. God knows what. I don't want to get into details, but anyway. So let's see, how are we going to decide if it's a min or a max? Tell me, we've done this. So imagine intuitively, right, the graph of a function. Imagine it goes up, up, goes down. At some point it hits a minimum. If it goes down, it goes up, right? So maybe something happened with the derivative up to that point, or maybe the other way around. It's down, it goes up, and then it goes down. So something happens to the derivative up to that point, and then something else will happen. So what that might be? Not quite. So what do we need to do to decide whether it's a min or a max? We'd like to see up to that point how. No, the double, maybe, okay. No, the double derivative will tell you about the concavity. We would like to see the min or the max. Well, actually, you can do the second derivative and you can plug it in. Yeah, you're right. But anyway, so we'd like to see, we'd like to take the derivative of the function up to that for values less than that critical number to see what's going on if the derivative is negative. Because if the derivative, for example, is negative, then the function is decreasing, right? So it goes down. And then we'll take our values. We'll like to see what happens to the derivative of our function for values greater than that critical number. If it's positive, then the derivative will go up. So the function is increasing. So in other words, let's see here. So we will look for values less than that critical number. And you can check this one out. And I'll leave it to you as an exercise. So here it's an exercise for you to see that when R is less than that critical number, right? Well, for example, when R is less than 5.42, then the derivative with respect to R is negative, so the function is decreasing, right? So it is decreasing, goes down, so it will reach a minimum, and then it will go all the way up to 5.42. And then starting from for values greater than 5.42, the derivative is positive. So the function increases. So that number there will be a minimum. This is how you prove it's a minimum. And exactly when r is 5.42, the second derivative, or like I said, so like Muhammad said, you can apply the second derivative. Why not? So this is the first derivative test. So here, if you want to put it this way, and this guy here is the second derivative test. So you can compute the second derivative of the function a with respect to r, and you will get 4 pi plus 2000 over r cubed, and this will be positive, and there you go. That will be an and then you evaluate this for r equals 5.42 of the critical value, and if it's positive, then by the second derivative test, there you go, it's a minimum. So in other words, we can say that A is a minimum when R is 5.42 centimeters and H is 10.84. That's it. See? So that was the, let me do another one, a similar one. Look at this one here. So we would like to, so another, so this is example 3. Let me just number them. And this is example 2. All right, great. So let's see example 3. So in this example, we would like to design a 1 liter oil that can be shaped like a right circular cylinder with the conditions that the material for top and bottom costs $5 per centimeter squared and the sides cost $2 per centimeter squared. Find the dimensions that minimize this cost. So that's what we need to do. So again, we need to draw a picture of relative quantities, and we need to find a formula for the quantity to be optimized, right? So here we need to pay attention. We need to read the statement very, very carefully, because you see in the previous example, right? Again, we're dealing with a circular cylinder, but in the previous example, we didn't ask anything about the material that we like to use for the top and bottom, which costs $5 per centimeter squared, right? So we only asked about the surface areas, and we tried to minimize that. But here, there is something. So we are trying to minimize the cost. So let's see. You see, this cylinder has two parts, so it has 2 circles, and then it's and the other part, right? So the circle, the area, we know that the area of each circle is pi r squared. So like I said here, we don't just want to minimize the area, we like to minimize the cost of the material used. So this is important here. That would be the cost function. So and let's read it carefully. So you see, the conditions is that the material for top and bottom cost $5 per centimeter squared. So the area of each of these, right, of each circle, right, is pi r squared, and also this guy here. So we have 2 of them, right? So, and we know that the top and the bottom cost $5 per centimeter squared. So the cost function will be, so let me write it here, will be C will be 5 because it, for each centimeter squared will cost $5 times 2 pi r squared. Great. And now plus, so we translated this so far. And now we would like to translate the other part. This one here. And the sides costs, or the sides, which will be this part here, right? Right, it goes like this. Cost $2 per centimeter squared. So this will be plus 2 times, and what is this, the area of that is 2 pi r times h. Great, so that is my cost function. So I need to deal with this. But as you can see at first, this looks like a 2-variable function, so maybe I should get rid of one of them. But maybe I know something at this point, right? And what do I know? Maybe I can express the volume. So maybe, so again, so in step 3, we would like to use the constraint to express the quantity in terms of a single variable, right? Because as you can see, this cost function at this point has 2 variables, R and H, and I don't like that. Like I said, we're not in Calc 3 here, and we don't want to deal with functions of 2 variables. So we like to only have 1 variable. So how we can express the constraints? So that is the question, and we should read very carefully. So maybe we can say something about the volume. What is the volume? The volume, right, is pi r squared times h, right? And we know that this is 1,000, right? So that's the constraint. And now, clearly, from this guy here, we can express h. We can write h as 1,000 over pi r squared. And now, guess what? What we're going to do? We're going to plug it into the cost function. We're going all the way here. Oops, sorry about that. We're going to plug it in right here. And now the cost function will be a function of a single variable. So let's do that. So again, h is 1,000 over pi r squared. And once we do this, we're going to end up with this. So this will be my cost function. So C of R, so this guy here, let me write it. This is C of R, or variable R, is this function right here, right? And this C is defined on 0, infinity, and real value. All right, so what do we need to do with this function? Can you tell me? You see, the magic word is that I need to minimize the cost. So what do I need to do? I need to minimize this function, C of R. So for me to do this, what do I need to do? We need to take the derivative of this, right? So let me write it. The derivative of this guy, C prime of R, so the derivative with respect to R is what? Is 20 pi R minus 4,000 over R squared. And the computations will be similar to the previous problem. And now we will, we're going to set this equal to 0, right? So again, that's the derivative with respect to R. We're going to set it equal to 0 to find the critical value. And now once we do this, we have to solve this equation here. 20 pi r cubed minus 4,000 over r squared equals 0. All right, great. So this will give us r to be the optimal values are this. So r is this guy, which is is cube root of 200 over pi, which is approximately, if you take pi to be 3.14, it will be around 4.00, and then h will give you this guy here. These are the critical numbers. So, and now we would like to prove that this is a min. How are we going to do this? Now you tell me. How are we going to prove it's a min? So we will show that what? So imagine graphically. So what do you want to happen for right in terms of derivative for something to be a minimum? So for values r less than 4, let's say, the derivative should be negative, right? So the function should be decreasing. It goes up, it goes down. So up, it goes all the way down. It reaches a minimum point, and then for values greater than 4.00, it goes derivative. The function, the graph of the function goes up. So the derivative will be positive. So in other words, we will have this. Again, you can check this when r is less than 4.00, the derivative of the cost function with respect to r is negative, sorry. So the function is decreasing. And when r is positive, is greater than 4.00, the derivative of the cost function with respect to r is positive. So that's the first derivative test. And then, so again, first derivative test. Or again, you can use the second derivative test if you want. You take the second derivative of the function. And then you plug in the value 4.00, and if it's positive, then it's a minimum. If the second derivative is negative, then it would have been a maximum. And that's it. So in conclusion, we can say that C is a minimum when R is 4.00 centimeters and H is 19.97. So that would be the optimal dimensions to minimize the cost. You see, this is like a real world application of this. Anyway, let's see one more example. So this was example, like I said, example 3. And now let's see one more example. And after this, I think I'll stop. And let's see this one here. Example 4. All right. So this has the following statement. Look at this. So a farmer has 1,000 acres of cotton. If harvested today, it would yield 600 pounds per acre, right? Unfortunately, weevils are destroying 7 acres per day. On the other hand, for every day it continues to grow, and the cotton that is left produces another 5 pounds per acre per day. So we would like to see when should he harvest the cotton. This is a little bit more complicated. So first, we need to understand the problem. And let's see, the step 1 is to see exactly, well, we need to label all the quantities relevant to the problem. Well, to draw a picture, I don't think it makes any sense, but at least we need to understand the quantities that we're dealing with. So we need to summarize all quantities in the problem. So, so today we have 1,000 acres and we lose 7 acres a day. Okay. So, and the total of today, this will yield 600, right, per acre, and we'd like to produce another 5 per day. So now we need to find a formula for the quantity to be optimized. So the way we're going to do it, so we know that the yield is the yield per acre times the number of acres. And now we can easily identify, it will be the yield per acre is 600 plus 5t, right? And the number of acres is 1,000 minus 7t. So that is my function. So I already identified my function, y of t. Is this guy here? And then we're going to do the same thing, 1,000 minus 7t. Whatever. And now we're going to do the same thing. So this is my function. Well, the domain will be, so this function y will be defined on 0, 1,000 over 7. And this will be a real value. So this is my function. Let me write it again here. So this is how it's defined. So what we need to do is what? Is we need to find the maximum of this function, right? So in other words, we need to take the derivative. As you can see, it's a product of 2 functions. So we need to apply the product rule. So for y prime of t, we need to apply the product rule. Right, because we have the product of 2 functions there. All right, great. So we need to find an optimum value, and we're going to do this. Like I said, we're going to compute the derivative, and I will leave this to you to figure out why the derivative looks like this. So like I said, here is the product rule. Right, so the derivative of y with respect to t is 600 plus 5t times negative 7 plus 1,000 minus 7t times 5. It's actually pretty easy to see. And we're going to set this equal to 0, and we're going to solve this equation. And once we solve this equation here, anyway, it will give us, t will be this value. I'll leave the details to you. So this will give us this. So t is 80 over 7. So that would be the critical number. All right, great. So now we would like to see to prove that this is a max. But now we can plug it in for y, and it will give us y, the value. So y of, let me write it here. Y of 11. Okay, let me write it like this. Y of 80 over 7 is, well, approximately is this value, whatever. 604.571 anyway. So that would be the critical value, right? And we'd like to see as step 5, we would like to prove that this is a max, right? How are we going to do this? in the same fashion. So we would like to see what happens for values of t less than 11.43. So maybe the derivative will be positive, right? So it's increasing. It goes all the way up to a point, and then it will start decreasing. So in other words, if you use the first derivative test, you will see that for values of t less than 11.43, less than the critical number, the first derivative with respect to t is positive, and for values here is not x, this is t, sorry about that, greater than 11.43, the derivative of y with respect to t is negative. So in other words, this is again the first derivative test right here. Or you can also use a second derivative test, which is right here. You compute the second derivative of y, and the only thing you need to do is just to plug in the critical number. And if the critical number, if the second derivative evaluated the critical number is negative, then that is a maximum. If it's a positive, then it's a minimum. So in other words, we can say that y, so this is a maximum, 604.571. It's a maximum, and it will be obtained at the 11.43rd day. Yeah. So this is how you deal with this kind of problems. Anyway, I think I'm going to stop here. Let me tell you one thing. So we have finished so far 4 chapters. So this concludes the chapter number 4. As you have seen, it's not just about computing derivatives. It's also about applying derivatives in different situations, so more qualitative properties of derivatives of functions. Now, we have only one more chapter left, which is, we'll deal with antiderivatives or integrals. This is again a very important chapter, and that will conclude the entire course. So the final exam, also the gateway exam, the second gateway exam will be about integrals. So you'll have to compute 10 integrals. But anyway, as we get closer to that, I'll tell you more details. All right, I think I'm going to stop here. Feel free to stop by my office. Also, I finished a bit earlier today, but feel free to stop by my office hours if you have any questions about the test or whatever, if you're unsatisfied with your grade. Anyway, we can discuss. All right, guys, I'll see you in like 20 minutes. Take care. Bye-bye.